Good afternoon, Professor.
Good afternoon, Karen. Awesome. Thank you. Good afternoon, Caitlin. Awesome. I love it. Yes. Good afternoon, Caroline. Good afternoon, Caitlin. Good afternoon, Amanda. I think that, yes. Good afternoon. All right. Awesome. Awesome. Good afternoon, Adan. Good afternoon, Kevin. Good afternoon, Estrella. Good afternoon, Amy. See, good afternoon, Erini. Good afternoon, Sumaya. Good afternoon, Erica. Awesome, awesome. Good afternoon, closed captions. Okay, we have like some serious math to get to today. We're still in the, hello. Okay, we're still in the context of the thing that is still on the docket as far as grades or things being due and whatnot is homework 2. There's not homework 2 is still on the docket. Some of you have done draft. Some of you have done 2 drafts. Some of you just noticed that my board is about to disappear, which it is. Yes. Okay. I mean, no. What I'm trying to say sort of quickly is that wherever you are in homework 2, it's still homework 2 that is on the docket. You could still, oh, and hello, Ruben. Hello. Hello, Euban. Hello, Rashman. Hello, Savannah. So it's wherever you are in homework 2 is still the deal right now. There won't be anything new assigned for a little while. I want to start finally making tracks through homework 2, which means that today I want to still talk about stuff that originally got motivated in question 9 from homework 1, got motivated in question 9 from homework 1, but then you've done a bunch of stuff in lab to start picking apart what's going on in question 9. And then you started doing homework 2, which is all this kind of exploration and different perspectives on really question 9 from homework 1B. Now, question 9 is a very big deal. It's not an accident that we spent a month or so leading up to question 9 on homework 1B. That is not an accident. I mean, it may be frustrating, but it is the case. Hold on, someone else is here. Sorry, speaking of frustrating, and my board is gone. Hold on, sorry. Many of you may already know the answer to question 9 in homework 1B, the numerical answer is 0.116 meters. I mean, that's the answer, but that's not the issue. The issue is everything that's underlying question 9. And the fact that you've done some equations in lab and seen some things is all great. And that's the way it should be. I mean, this is a science class and this is science. So we learn things by investigation and discovery, and experimentation and failure and frustration. And we eventually land on ways of cleaning up the material and resolving issues and putting them together in lecture. So anything that you've picked up from lab or picked up from homework 2 already is great and hopefully very helpful. But if you're still don't feel that you're totally there yet, that would not be surprising. I have not really explained. I have not at all explained the importance and the solution method for question 9, homework 1B. I started it last Wednesday, but that's where we're going to continue today. The ultimate goal of question 9, homework 1B, the ultimate goal is to get to equations that look like the ones that are on the board right now. That's the goal. Question 9 is about x's and t. What's on the board here is about z's and t. You'll ultimately see why we ultimately make that generalization or that change. I mean, that'll all come out in the wash. I'm here to say again that I'm here to unpack what's going on in question 9, homework 1B. And once you see everything I have to say about question 9, you'll see how a lot of homework 2 is just repeated exercises and perspectives on this question. They might still seem very hard to you right now. And that's why and that's totally fair. If they all seem hard and mysterious or weird, or maybe you have them, but you're not sure, that's all fair. And same thing with the labs, all fair if things are a little bit, I don't know where for you right now. But now I want to finally start unpacking all of that and explaining it. So So that's what we're going to do. But bottom line, there's no new homework besides homework 2, just wherever you are with that, just keep going with that. And by the end of this Wednesday, I think you'll have seen a lot that will really help you with homework 2. Okay. And stop me if, so I'm a little bit intense about this because we're finally getting to like a place in the material that I think is very exciting to me, but also can be challenging to people. It's very mathy. So if I'm yelling, it's because I'm excited and intense, not because I'm angry. But if I've already lost you or you have other questions that are logistical about assignments or grades and I forgot, please put them in the chat. I mean, and I am going to ask you to participate big time in the chat today when we get to certain moments. Anyway, all right, so here we are, right? We're all in the context of homework 1B, number 9. It's also in the context of homework 2. It's in the context of recent labs. We're trying to unpack what's going on with this seemingly simple system of a mass oscillating back and forth on a well-behaved Hooke's law obeying spring. The question that was posed in number 9 was the seemingly straightforward question: when t equals 1 second, what is x? Like, where is the mass 1 second into its oscillatory motion? Now, I want to say on the one hand, that is a very fair question to ask. I'm not saying it's easy. It's actually not easy, but I'm saying it's a very fair question to ask. It's the central question of physics once I put it in general terms. That is to say, question 9 on homework 1B, which, was something that was put on a sheet like a long time ago. Question 9 sounds like super specific. At t equals 1, solve for x. Now, again, the super specific answer to that question turns out to be 0.116 meters. But that's not really the issue. The reason I'm spending so much time getting to this question, and that I'm going to spend so much time talking about the question after the fact, is that the real issue is not the number 1 or the number 0.116 or any of the details of this problem. The real issue is not that K is 200 newtons per meter or anything like that. The issue is that we're asking, what is x as a function of t? We are asking, if you name the time, can I name the space where something is going to be? And that is the fundamental question of physics. I want to argue right now to you, if I haven't said this before, all of physics is a study of stuff moving through space and time. All of physics is stuff of one kind or another, maybe particular, material, tangible stuff, i.e. physics 203, or maybe ultimately more intangible stuff like information or energy or sound or heat or light or electricity or something. But whatever it is that we're talking about in physics, we're talking about bits of something being in some space at some time. And all we're ever trying, in other words, we're always talking about kilograms in seconds and meters, ultimately, MKS, right? It's not a coincidence. So ultimately, the question in any moment in physics, in any branch of physics, in any century of physics, the question is always, given some point of stuff, if you name the point in time, can I name the predicted or retrodicted point in space? Or some version of that. Or maybe if you name the point in space, can I name the point in time when the object's going to arrive at that point in space? But this is always what we want in physics, is ultimately x as a function of t, or some version of that. The only thing that makes one topic of physics different from another, or one chapter of physics different from another, or one investigation of physics different from another, is what conditions we impose on this question of x as a function of t, okay? A lot of physics 203, a lot of physics 1, the basic condition that we're imposing is constant acceleration. And one big example of that is free fall. A lot of physics 1 has to do with predicting x as a function of t, assuming that a equals a naught. Assuming that a is some constant such as 9.8 meters per second squared, right? In other words, a lot of physics 1 was we have to figure out x as a function of t, assuming that the derivative of x as a function of t was a constant number, a constant value measured in meters per second squared, such as 9.8 meters per second squared, right? Okay, so that's one example of a topic of physics. But notice what I'm trying to say right now is that what defines a topic of physics is the constraint or the condition or the assumption that we impose on the larger question, the restriction that we impose on the larger question. Can we find x as a function of t? Can we find some rule that maps time as an input and maps out position as an output? Okay. The condition in front of us now, the condition of the mass on the spring is Hooke's law, elasticity. We're now assuming that F equals negative kx. It's a pretty simple sounding condition. It is a pretty straightforward, it's a linear equation. It's a straight line equation. And it doesn't even have a y-intercept. It's just F equals negative kx. That's our condition by virtue of which we want to predict what x is as a function of t. So we're going to solve this. So we write down, so if I were, so I'm, in effect, I'm solving question 9, homework 1B. What are my GDPs? What are my step 3 GDPs? Well, F equals negative kx, because that's the law that governs the elasticity, the elastic force exerted by a spring. And then I'm writing F net equals ma, because that's always a law in physics, Newton's second law. That's the way all forces work. So I put them together. I say, okay, in this case, there's only one force acting on the mass. It is the spring force. Therefore, the spring force is the sum total of all the forces. So negative kx gets plugged in for the net force, negative kx equals ma. But then I say to myself, A, what is A? A is instant. Oh yeah, that's the word but. That word that you can't read next to the ma is the word but, B-U-T. Excuse me, hold on a second. Okay. And this, the other word is so. So I say, A doesn't have a bar over it. It's instantaneous A. It's not average acceleration. It's acceleration at a point in time or in the limit as the time interval approaches 0. So the definition of A is the instantaneous rate of change of velocity. And the definition of velocity is the instantaneous rate of change of position with respect to time. So acceleration is the derivative of position with respect to time. It's the second derivative of position with respect to time, right? Okay. That's what this means. So notice, before I go any further, okay, so I'll say, so I plug that in, so I have negative kx equals m d2 dx over dt squared, and then I just rearrange in sort of not that you like literally have to in order to solve, but to make it sort of look like a customary, nice, pretty physics equation. What we tend to do as physicists, and mathematicians do this too, or some version of this, we tend to like to collect all the constant terms and put them together to make it clear to us that certain terms are just letters that are just standing for unchanging numbers. K is an unchanging number of, in this case, 200 newtons per meter, but in some other case, it would be 150, whatever, but it doesn't change throughout the problem. And M, same thing, stands for the mass. It could be one mass in one problem in one experimental apparatus. It could be a different mass in a different experimental apparatus. So we leave it as a letter to leave this general, but it's not, but it's a constant, right? M and K are constants. So I put them together in the parentheses. And I have a statement now that says d2x over dt squared equals negative k over m times x, right? Negative constant times x. So I have now the information that I'm looking for. In a way, I have the information that I'm looking for. I have an equation, I have an expression that has a bunch of letters in it, but there's only two letters in it that stand for variables, and those are the two variables that we're interested in here, x and t. And I can tell by the way that derivative is written, I can tell that since x is in the numerator, it is being treated as a dependent variable, right? That's a standard notation for derivatives, that an instantaneous rate of change is really a rise over a run. And what we mean by rise is the change in the dependent variable. And what we mean by run always is the change in the independent variable, right? So just the left side alone makes it clear to me, even if I don't know at all what's going on here, like even if I didn't do all this because I just was walking through the forest and I slammed into that equation, the left side would make it clear to me that t is being treated as an independent variable and x is being treated as a dependent variable. X depends on t. And there's no other variables in this equation. So in a way, this contains the information that I'm looking for. Remember, what are we looking for? And it's very easy to forget this, by the way. It's very easy. Not even, especially when I'm talking, but even if I weren't talking and this were a textbook or something. Remember, the issue here is we're looking for x as a function of t. We're looking for some rule that maps x to t. Like in the particular example of question 9, we're told that t happens to equal 1 second, but it could have been anything. We would be able to solve question 9 as long as we had some equation, what you might call a formula. I hate that word, but we're looking for some equation for which we could plug in a t value and it would pop out an x value. That's what we don't have, is the appropriate equation. That's really what we're trying to find here, is some equation that links x to t. We're looking for x as a function of t. Now, this thing that we just landed on at the bottom of the page is good news in a way. It's good news because the only variables it has going on in it are x and t. And it is treating t as it should, as some kind of input. And it is treating x as some kind of output, but treating in the very loose sense of the term. But it's not a rule that I can use to get an answer to this question. Like I literally cannot just there's no way I can literally plug in 1 for t and have it pop out some x value. What this equation is saying, it's saying, you want to know what x is? Yaberbaum, you want to know what x is? You want me to tell you t? And you know what x is? Well, here's what I'll tell you, says the equation. The equation says, I'll tell you that the rate at which x changes, the rate at which it changes, it's a double rate, right? Because it's a second derivative. So what this equation is saying is the rate of change of x with respect to t is the following function of x. That's what it's saying, right? It's not saying if you plug in t, you'll get out x. It's saying if you plug in x, you'll get out the derivative of x with respect to t. That's very different. That's a very different input-output rule, right? So it's got the information that I'm looking for, but the information is packaged in a very exotic way. My goal here is to unpack that information, to somehow unwind the derivatives that it's posing and get back to the original function of x as a function of t, okay? It's instead of giving me x, so remember, I'm trying to solve for x as a function of t, and in some ways that's what I'm always doing in physics. But I don't have x as a mapping to t. You might even say, and I almost hope that some of you are thinking, you might even say, wait, but don't we? I thought we had an equation for x and t, like back from physics 1. He keeps bringing up physics 1. Didn't we develop x as a function of t in physics 1? We developed more than one example. One big one that we developed in physics 1 was x equals 1/2 at squared plus v naught t. That was a big example of an xt function. That was great. But that assumed that the second derivative of x right? That assumed acceleration was constant. That assumed that A was some unchanging number that could be plugged into 1/2 at squared plus v naught t. In other words, this is exactly what I'm saying, is that the condition of physics 203 was not just any old condition. Actually, it was a condition that had to do with derivatives. The condition was that the derivative of position with respect to time was a constant. Given that, we found that x equals 1/2 at squared plus v naught t. In effect, without knowing it, in physics 203, what we were really doing a lot in a way was we were given information about a derivative and working backwards from that to get and then use an equation about the original function. And that's what's happening here too, but it's a different condition. In physics 203, the condition was d2x over dt squared equals a constant. For example, 9.8 meters per second squared. And notice, I've got to go a step further. The condition of physics 203 a lot of the time was that the d2x over dt squared, in fact, I'm going to add a page here right there. 1 second. Okay. In physics 203, we got equations like x equals 1/2 at squared plus v naught t, because the assumption was that the derivative of x, the second derivative of x with respect to t, was some kind of function of t. It happened to have been a constant function of t. It happened to be a horizontal line in time, 9.8 often. I mean, not all the time, but say in free fall, 9.8 meters per second squared. Notice, not only we were given some function of the derivative. We knew what the derivative of x with respect to t was doing in time. What it was doing was equaling some sort of constant number in time. That constant number was like 9.8 meters per second. Like it was still treating, in other words, time as the independent variable. So then we in effect integrated twice. The integral of a is at plus v naught, if you think about it. And the integral of that is 1/2 at squared plus v naught t. That might be going a little fast for some of you, but if you just do the power rule backwards, you'll see what I'm saying. But I'm saying here, we have a different expression now. We have that the second derivative of position with respect to time is equal to some constant times, not even times time, but times position, times x. And this now makes all the difference in that. This is a new equation that we have to solve. This is not an answer. This is a question. The question is, what is x as a function of t? The question is, how can we get from this derivative information to X information, like directly speaking? And what I'm here to tell you is that just integrating, just doing an so what I'm telling you is you have a derivative of a derivative, but we're looking for the original function. If you've been following calculus for the last couple of years, or following what we've been saying in calculus for the last couple of weeks, what might be going through your brain, and I almost hope is going through your brain at some level, is, okay, so we're looking for the function and we're given some information about the derivatives, like about the derivative. He's telling me the second derivative. He's telling me the derivative of the derivative, but I need the original function. So he doesn't want me to take derivatives. I already have taken the derivatives. He wants me to go backwards and see the original function, find the original function. And you're right if you're thinking that. And if you're thinking anything like, well, then I guess I sort of have to anti-differentiate somehow, you're right. But but if you think we can just directly integrate this, it's not quite that simple. If you're thinking that somehow we have to differentiate backwards in some way, if you're following me at all, you'll understand that I'm saying we have derivative information, but we're looking for the original function information. That calls for somehow thinking about derivatives backwards. If you're thinking that, you are correct. But it's a little bit deeper than simply doing an integral. And that's what I have to show you right now. Well, actually, all right. So this is wait, let me just think for a second. Let me just ask. Yeah, wait, I'm not gonna. I don't need this page. Did not mean to, sorry. I was about to go off on a sidebar, but I'm actually going to resist the temptation. And I don't need this page. No sidebar. No sidebar. I'm exercising amazing self-discipline here. All right. So this. Oh, and we just lost the board, I think. Yes, of course. Hold on. So what I want to say is this. As soon as I get the board back. Okay. What you will notice is, okay, what we have here, what we have in this expression, like the expression we have is this thing in red at the bottom, I mean, circled in red. We have d2x dt squared equals negative km over x. We have the derivative of x with respect to t is some function of x. Our goal, please remember, our goal, I cannot emphasize enough, but I'm going to try. Our goal is to get x as a function of t. Partly because that's what question 9 is really asking us. It's asking us for some rule where we plug in the t and out comes an x. But also we're doing this because this is the thing to do in physics in general. So what we have here is the derivative of some dependent variable. We have the derivative of x with respect to t being expressed as a function of the dependent variable, not of the independent variable. In other words, what I'm making a really big deal, what I want to say is this expression right here. Notice that on the right side is an x, not a t. That makes all the difference in the world. Let me say this again. The right side is an x, not a t. Now, I understand they're both just letters, and I understand they're both just variables. And I understand that any letter could stand for anything, and any other letter could stand for anything. But in this case, if you look at the left side, we are definitively treating t as the independent variable, as the measurement that's driving the phenomenon, as the measurement that is, loosely speaking, the cause of the phenomenon. And X we are treating as the dependent variable, right? As the effect of the cause. And this expression says that the rate of change of effect with respect to cause is some function of not cause, but of effect itself. I might have maybe lost one of you when I just said that. And if you were with me until right when I said that, and then I lost you, then you're actually very much with me. Because if something about what I just said is slightly confusing to you, you get the issue here. Let me say again, and I know I said this Wednesday, but I cannot emphasize this enough. It took me years to realize, I mean, I didn't discover this. I mean, this is a standard thing, but I was blocked personally on this for years. So there may be at least one of you in the room who's also blocked on this. What I'm saying is that equation at the bottom, okay, let me back up for a second. Our goal is to know where the mass is as a function of time. We want to know where the mass is at any given second. Right? So we walk in there and say, well, we're physicists. We're physicists. We want to know where the mass is at any given moment. So we know how to do physics. If you Yaverbaum, or you experimentalist, or you magazine publisher, if you could just tell us what the acceleration of this thing is doing. I remember from old physics, if I know acceleration, that's a way of predicting position. Like I have rules that relate acceleration to position. Acceleration, after all, is just the rate of change of position with respect to, it's kind of like saying, I know rate, I know distance equals rate times time or something. Like if you just tell me how fast the car is going, I know where the car is going to be in an hour. Okay. Oh, the car keeps changing its speed. Well, if you just tell me the rate at which it's changing its speed, then I'll be able to figure out what its speed is in an hour. So I can figure out where it is in an hour, right? That's like the heart of physics. I want to know where the mass on the spring is. So I'm just saying, can you just tell me what the rate at which it accelerates is? But this equation says, oh yeah, we can tell you the rate. Oh, you want to know the rate at which this thing accelerates? You want to know the rate at which it changes? The rate at which it changes? Where it is? Oh, we'll tell you. It's a simple function of where it is. That's what this says. It says, you're telling me that in order to figure out where the thing is, you need to know the acceleration, because that's what we always do in physics. And we're telling you the acceleration is based on where it is. It's a circle. If you think I just said something circular, then you're with me. You get it. I'm going to say it again. We want to know where the mass is at any given moment in time on the spring going back and forth. We want to know where the mass is. Standard physics approaches just tell us the rate at which it's accelerating. And from that, we'll be able to figure out where it is. But this thing says the rate at which it's accelerating is based on where it is. If that makes no sense to you, join the club. It doesn't make any sense. I mean, it's ultimately solvable, but it's actually miraculous that it is. It is self-referential. It is actually that expression. If you look at it and you see that the rate of change of position with respect to time is actually dependent on not time, but on position itself, the fact that the right side is an X rather than a T means this thing is referring to itself. It means that actually it's embodying what we know in physics, what is known in physics and math to be called feedback. This is a feedback phenomenon. The most extreme version of feedback that you know in daily life is if you stick a microphone too close to a speaker, right? The sound comes out of the speaker into the microphone, but then comes out of the speaker into the microphone. The thing causing the phenomenon becomes the effect of the phenomenon and vice versa. And so it feeds off each other, and next thing you know, right? Like me right now. I'm saying that what we're used to in physics is some rule about acceleration. We're used to the idea that the rate of change of position with respect to time is somehow based on time. That we know how to unpack. That you can do derivatives backwards. You can take integrals and do that. But this says that the rate of change of position with respect to time is not based on time. It's based on position. It says that the rate of change of effect is not based on cause, but based on effect itself. It's a loop. Whenever you have this kind of situation whenever you have an equation that doesn't just have a derivative in it, but where the derivative is actually a function of the dependent variable, where the rate of change of output is not based on input, but based on output itself, that is called a differential equation. Okay, a differential equation is not, meaningfully speaking, a differential equation is not just any equation that has a derivative in it. Equations that have derivatives in it, we can work backwards. We can anti-differentiate. We can integrate and get functions. But one of the reasons that I had to slow down or bore some of you and like sort of re-explain how derivatives work and how integrals work, because I wanted you to have some fresh memory of derivatives and integrals at your fingertips, because now we're about to do something even more advanced. We're about to look at something called a differential equation, which has sort of the challenge and the intrigue of integrals, but is one step more abstract. It's not a direct integral. A differential, so I'm going to say again, a differential equation is what it says on this board. It's not a joke. I mean, well, it's certainly not a joke. It's not funny, but I mean, it's not super easy until you get used to them. A differential equation is an equation that links the derivative of some dependent variable, the rate of change of some dependent variable with respect to some independent variable, it's an equation that expresses the derivative of a dependent variable as a function of the dependent variable itself. That's what a differential equation is. Now we have to look at this one. We have to look at others in this class. I have to now say, so this is some calculus. It requires some comfort and command with basic calculus, derivatives, and integrals. That's why we refreshed that. And that's why we reminded ourselves and looked at those things in a physics way. Now we're getting to something called a differential equation. Let me be very clear. We need to do some differential equations in this class. You were not required to have a course in differential equations before coming to this class. A class called, many classes exist that are called courses in differential equations. They exist. None of those classes was a prerequisite for this class. You were not expected, or you're never expected or required to have already had a course in differential equations in order to walk into this class. You're also not required or expected to have a course called Physics 204 in order to walk into this class, right? Like, you walk into this class, you don't have a prerequisite or a background in Physics 204 in order to come to this class. In this class, we're expected to learn Physics 204. Okay, same thing with differential equations. You weren't supposed to have had them already. We're going to learn them together. Not going to learn all of them. We're not going to learn everything there is to know about them. We're going to learn certain differential equations from the bottom up that we need for physics, just like we're going to learn certain physics that we need for physics. It's expected that you have enough calculus to be able to attain this level. This is where we get into the realm where I personally believe it's actually easier to learn math with certain physics prerequisites than the other way around. So I want you to join me in appreciating that we're about to recognize and unpack certain differential equations. You can all do it. I've done this for many, many, many years in this class. We can all do it. It's not beyond any of you at all, but it will only work. You'll only understand what's going on with these differential equations if you first clear your mind, open your mind, and recognize I'm not talking about things that I think you've already heard. I'm not assuming you've already heard this. I'm assuming that we can hear it together for the first time. So I'm just changing the view so I can see who I'm talking. Okay, so first thing I'm saying is, just because an equation has a derivative in it, that alone does not mean it's a differential equation. If an equation has a derivative in it and the derivative is linked to the dependent variable, then it's a differential equation. How do you know what the dependent variable is? Whatever's in the numerator of the derivative. Now, this equation that we're going to look at here, this equation, it happens to be a second derivative. So technically, this equation is technically called a second order differential equation. Why are we beginning with second order differential equations when we've never studied first order differential equations? Because that's the way the physics works. These were the first differential equations that any physicist ever like encountered, and they had to figure out a way to develop the math that made sense to solve these. That's what we're going to do. Okay, so this page is just a repeat of what I just said. So I'm saying a differential equation does not equal, by definition, an equation with a derivative in it. They can overlap. I mean, certainly any differential equation is an equation with a derivative in it. But I'm saying specifically, a differential equation is one that links a derivative to the dependent variable. So the one that we're looking at here is the one in black at the bottom. We're looking at d2x over dt squared equals negative k over mx. It's a differential equation because it doesn't tell us x as a function of t. It tells us the rate of change of x with respect to t. And it tells us that that rate of change is somehow dependent on the very thing that is depending in the first place, x. By the way, another example of all this, just really quickly, I am yelling because I do think this is a big, I think it's really worth paying attention to this. And I'm going to turn it over to you guys in the chat in a couple of minutes to make sure we're all together on some of the basics here. But this is also very similar to if you've seen this before in other math classes, like if you have a bank account that compounds interest, like an interest-bearing savings account, right? Where you get like 1.25% interest on your money, every month or every year or every day or whatever. So what does that mean? It means you walk into the bank and you say, how much money do I have in my interest-bearing savings account today, ma'am or sir? And they say, oh, you want to know how much money you have in your account today? Well, that depends on how much, like you have more than you had yesterday. The amount and you're like, yeah, cool. And they're like, the amount that you have today, it depends on how much interest we put in last night. It depends on how much we added to your account last night because you get interest and you're like, cool, great. So they're like, so how much money you have in your account today depends on how much interest we added to your account last night. And you're like, great. So how much interest did you add to my account last night? And they say, well, it depends on how much money is in there, right? I mean, this is true. I'm not trying to mess with you. I'm just trying to make it clear. That's an example of a feedback phenomenon. And other things too, population growth, radioactive decay. Anywhere in math where you ever got into exponential functions, right? These are all feedback phenomena where the rate of change or the rate of change of the rate of change, whatever, where some derivative, some rate of change of the effect with respect to cause is a function of the effect itself. How much money is added to your account depends on how much money you have in your account. And how much money you have in your account depends on how much money was added to your account. That's what's happening here. Where the mass is depends on the rate at which it's accelerating. But the rate at which it's accelerating depends on where it is. It's actually an extraordinary kind of weird logic. It's like two mirrors facing each other. Like, what do we see? And I'm not trying to confuse anybody. I'm trying to point out that it is an exotic, strange phenomenon. And it's actually shocking that we can ever pull it apart and get any kind of answer. Often we cannot, but sometimes we can. When we can, it's known as solving a differential equation. To solve this differential equation, d2x dt squared equals negative k over mx, to solve it doesn't mean to get a number. I mean, we will ultimately get a number once we ultimately evaluate our function. But first and foremost, to solve this differential equation, we're going to get a function, right? Remember, function means number in, number out. Operation means function in, function out. This thing is telling us the derivative of the function is blah. We got to find the function. We got to find what x is doing as a function of t. What does that mean? It means we've got to find some function x, some rule that maps x to t. We've got to find some rule such that when you take the derivative of that x expression, apparently we're going to get back that x expression times k over m times -1. That's what we're looking for. We're looking for an x such, right? I'm reading the black at the bottom. I'm saying to everybody that a differential equation it's an equation, but it's not an answer. It's a question. It's inviting us to do reverse engineering. It's literally like Jeopardy, like, you know, where you get the answer and you have to figure out what the question was. That's what's happening here. If you're ever used to thinking that physics questions are solved once you have the equation to plug in, this isn't that sort of equation. This equation is leading us to try to find out what the proper equation is. And I'm going to say again, I know I'm yelling. It's not because I'm upset at him. It was just because this is a big thing. And because I just know that I did not get this for years and years. It doesn't mean you don't. And those of you who already get what I'm saying, like, I'm psyched and I'm not trying to yell at you or anything, but I just know that when I didn't get this for years, I didn't get that I didn't get it. I didn't think I didn't get it. I didn't know that I didn't get it. I thought I got something, but what I got was wrong. And I'll show you exactly what I was wrong about, like, when we get there. What I'm saying now is this is reverse engineering. We're looking for an X such that when we take two derivatives of it, we get back it times K over M times a -1. Like, literally, when we take two derivatives of this thing that we're looking for, we get back the thing we're looking for. We're looking for a thing that when we take two derivatives of it, we get back it times K over M times -1. If you just heard me say that, but you're like, all right, I heard that and I get that he's yelling and I get that he's saying something that he thinks is important. I feel like he said it 40 times already, but like the thing he just said, like, where did he even get that from? I got it from the black writing at the bottom of the board. Like, it literally says, right? It says the derivative of X is equal to, just read it backwards, is equal to X, but times K over M times -1. So it's saying I need a function, which when I differentiate it twice, I get back itself. That's what it's saying. Now I got to find that function. I don't know how to find that function yet. It's not a joke. It's not easy. There's no clear path to finding that function. If I were a mathematician, I might want to take like 3 courses on this to figure out different techniques and different experiential like tricks and tools for figuring out what that function is. But the thing is, I'm a scientist. You're a scientist. We're physicists. There's a reason that we've been poking around in the lab for 3 weeks before we even got this, and poking around with other examples, because we're experimentally trying to get some sense of what kind of function would describe a mass going back and forth on a spring. We've actually collected a lot of data and made a lot of graphs to get a sense of what is position doing as a function of time for a mass on a spring. I'm just looking at the time right now. I'm going to skip right now in the pages. I'm going to go back and say, but I'm going to say, just in case I'm losing anybody or boring anybody, which of course is distinctly possible. Let me just say, to skip to a chase. I'm going to go back to all that in a moment. But like, if you think about everything that you've been playing with in the lab and other examples and examples from homework 2, what we've been trying, and questions 6, 7, and 8 on homework 1B, what we've been trying to establish to ourselves is that something that's going back and forth on a spring is going back and forth smoothly on a spring, right? It's starting at a certain position. It's coming down to the equilibrium. It's going past the equilibrium all the way to an equal point on the other side, then coming back up to equilibrium and going back and forth, et cetera, et cetera, et cetera. And it's doing it in a smooth way, right? As it gets closer and as it gets closer and closer to equilibrium, the rate of change, the velocity is getting faster and faster. In other words, if we were to plot position as a function of time on coordinate axes, we would notice that as the position was getting closer and closer to 0, the slope of the graph should be getting steeper and steeper, either in a positive way or a negative way, but the slope of the graph should be getting steeper and steeper. And we should notice that when the point is getting closer and closer to amplitude positions, such as x0 or negative x0, we should notice that the slopes of the graph should be getting more and more horizontal. The velocity should be getting closer and closer to 0, right? You see what I'm saying? And then we should see that we should expect that all of this is happening smoothly, that nothing is happening discontinuously, so that if something is going back and forth on a spring, it should be doing it in a smooth oscillatory way And the graph should look something like what I just drew here. And don't even overstress about the exact answer that I wrote below it yet. I'm just saying right now that part of the reason we've been messing around in a lab for a while before actually landing on this answer is to start building up an intuition and some experimental data that would suggest that the type of function that would solve this differential equation might very well be some sort of cosine function. I'm just saying from an experimental point of view, and don't get bogged down, don't worry about what's in those parentheses just yet. I mean, unless you want to, but just look at the fact that if your time for the last 3 weeks has been spent on anything, it's been spent on trying to build up an intuitive or experimental picture to suggest that the type of function that would be a solution to this differential equation would be some type of cosine function, some type. Don't worry about the details yet. I'm just saying some type. The solution to this differential equation, I might guess, is some type of cosine function. I would guess that in an educated way as a scientist who's collected a bunch of data on this phenomenon. This is, in fact, why we are scientists, not mathematicians, that we do things in the lab first to build up educated hypotheses or conjectures for math problems that we're trying to solve. Now, I haven't proven a thing. I actually jumped, you might notice I jumped ahead many pages in the notes today, just to say that what we're gonna do is to say that there's no clean, direct, algorithmic or linear way to arrive at, to procedurally solve for the solution to a differential equation. There are ways of building up experience, experimental technique, or mathematical technique for arriving at educated hypotheses or conjectures as to things that might solve differential equations. And then what we have is a method for testing, for verifying our possible conjectures. I'm saying now, and one way that we come up with these conjectures is from the lab. And one conjecture that we're ultimately going to come up with for this differential equation is some kind of cosine guess. But I'm saying no matter what we do to solve a differential equation, no matter what we do to solve a differential equation, is we do some some version of guess and check. We are and that is scientific. That's not because we're students. That's not me leaving something out. That's not me condescending or something like that. The differential equations are just tricky enough. They are just feedbacky enough that the way to come up with solutions is to conjecture and verify. That's what I'm going to show you right now. The first thing and I know I'm getting abstract. This is mathematically abstract. Bear with me. We're about to get a little bit more concrete. The concrete thing I'm trying to say right now is we need to solve this differential equation. We need to get an X that works, that satisfies this description of X, of d2x dt squared. We want, so we're trying to solve this. Again, if you want to keep things super concrete, I'm trying to solve question 9 in homework 1B. I'm trying to come up with some XT rule that will allow you to plug in 1 second for T and spit out an X. But I don't have that rule yet. What I have is the physics what I have is a differential equation. The differential equation is leading me to try to figure out the function. We want an X equals f of T. We want X as a function of T such that so I'm just reading the board right now, such that the second derivative of X with respect to T equals negative K over M times X. So once we find and yes, I just skipped ahead a few pages and you sort of saw the answer, but I didn't explain at all where I got that answer from. And I didn't show you why I know that answer is right. I'm just giving you a sneak peek to say that ultimately our correct answer is going to kind of come from the lab. And that's why you did labs first. But let me tell you what I mean by a correct answer. When we find a correct X as a function of T that satisfies the condition of the differential equation, we will say we have solved the differential equation. In other words, the solution to a differential equation is output expressed as a direct rule or function of input. The solution is not a number. The solution is a direct function. What does it mean for it to be a solution? It means that the solution is consistent with or fits or satisfies the original differential equation. Again, I'm going to say it. We're looking for an x such that the second derivative of x with respect to t is x itself, but times k over m times -1. We're looking for an x that satisfies that condition, the condition of the differential equation. So what do? What we do is, well, okay, so this board says again what I just said. Hold on, I'm just going to change the view so I can, and I am going to, just to warn you, I know we are going to finish this today. I mean, I finished in the other class. We have 20 minutes. I'm warning you that, I'm warning you that in a minute or two, I'm going to ask you a couple of exercises that you're going to do in the chat, just so don't get a cup of coffee yet or whatever. Or I'm also, it's not that I'm warning you, but I'm also letting you know it's going to get concrete in a minute. If it's all like very heady right now, it will be more concrete in a minute. But what does it mean to have a solution to a DifEq? It means to have a function which satisfies, which fits, which is consistent with the DifEq. Okay, that's what I'm saying. So what I'm going to do now is, again, I'm saying where we come up with possible solutions, we come up with them from educated guesses. Our educated guesses either come from mathematical experience or they come from scientific experimental data collection experience in the lab. Once we have a guess, then we check the guess. And that is something we can do algorithmically, concretely, procedurally. Like the art of coming up with a guess is the art part of this. But once you have any kind of guess at all, you can check very cleanly and in a very organized, concrete way, you can check whether your guess is right or wrong. You can, in fact, you can find out that it's right, which is lovely, or you can find out that it's wrong, but if you know what you're doing, you can see how wrong it is and start playing with it to make it right. So this is a very kind of like trial and error kind of thing to do. It's a very experimental branch of mathematics, even when it's just on pen and paper. So I'm going to show you an example now of, to make it clear to you what it means to be a solution. I'm going to show you a guess now that would be a very reasonable guess that many of us might have made, especially if we pay attention in Physics 203. I'm going to show you a guess that's a reasonable one to guess, that has all the right form to it, but that in fact does not satisfy the differential equation. I'm going to show you a counter example on purpose so that you can see by counter, and then I'll show you the real thing, so that you can see by contrast what it means to satisfy the equation or not. So here's what, and this is where you're going to come in. So I'm going to conjecture. I'm going to say, you know what? I've been in physics for a semester and a half. I'm used to xt functions. We had this function back in the day, x equals 1f at squared plus v naught t. That's an xt function. That is plug in t, get out x. And that's helped me a lot in Physics 203. Now, in Physics 203, it had to do with A and V naught. Here, we're in this problem with a mass on a spring. So what I'm going to do is I'm going to take that old expression and I'm going to say that had the right form. And it does. I'm not tricking you. I'm telling you straight up that this would be a very wise guess. X, I have a statement here in blue at the top of the page where the only two variables are X and T. T is being treated as an independent variable. X is being treated as a dependent variable. And everything else in there is either a straight up number or is a constant. In this case, the constants are K and M. So this has like all the correct features that I'm looking for. K is a constant in there. M is a constant in there. T is an independent variable. X is a dependent variable. It looks like it totally could maybe work. And it's a good standard physics kind of format. So I'm being a good, reasonable citizen. And I'm guessing, I wonder if x equals 1f kt squared plus mt is like the equation Yaverbaum was looking for here. I wonder if this is a solution to the differential equation d2x dt squared equals negative k over mx. This is a very reasonable, educated conjecture, okay? Now what I'm going to show you to do, what I would do with this conjecture is I would check it or I would verify it. How? By taking derivatives. This is where you're going to come in. And I know we have 16 minutes. What we're going to do is take derivatives of this. Derivatives. We're going to take a derivative of it, and then we're going to take another derivative of it. Why are we going to take two derivatives? Because the differential equation is a second derivative. It says we're looking for an x such that when you take two derivatives of it, you get back itself. Like literally, we're looking for some expression which when you differentiate it twice, you get back the original expression times k over m times negative sign. Why do I keep saying that? Because our differential equation is d2x over dt squared equals negative k over m times x. It literally says when you take two derivatives of x, you get back x, whatever x is, times k over m times a negative. So we're looking for an x, a rule of x as a function of t. We're looking for some x expression, like not a number, an expression, a function. We're looking for an x that does that when you differentiate it twice, you get back itself. So I'm going to try this x. I'm going to see if when I differentiate it twice, do I get, in effect, negative k over m times 1f kt squared plus m over t and m times t. If I do, like hopefully some of you are with me. If I take two derivatives of this thing that's in blue at the top, and I get back negative k over m times 1f kt squared plus mt, then I win. That's what I want. Something that gets back itself times negative k over m. But let's see. What I'm going to ask you now is I'm going to change the view. I'm going to ask you in direct chat, please, like not public chat today. Okay, in direct chat, I want you to take one derivative of the x expression at the top. Like x is the dependent variable, t is the independent. So it's like and everything else is a constant. So it's like I'm saying, what's the derivative of y equals ax squared plus bx or something? Except instead of y as a function of x, I'm saying x as a function of t. Like honestly, this is some practice here. And I want everybody to tune in. I want in the direct and submit all this for points. Hopefully you see you're getting all your points for all these things these days. Please, in the direct chat, in other words, what I'm asking for. Yeah, here it goes. Like I'm supposing we're conjecturing the top that x equals 1f kt squared plus mt. That's our function. T is the independent variable. It's like x in a math class. X is the dependent variable. It's like y in a math class. Everything else is like a number. I want you, please, like now, it's participation time. I want, and I'm yelling again, I'm not angry, but I am intense. I know, because I'm not asking you to solve a differential equation. I'm asking you to take a derivative. I'm asking you to check my possible answer for this differential equation. So I want dx over dt for this function up here. Your answer won't be a number. It will be, you'll write on the left side, you'll write dx divided by dt and equals. And on the right side, you'll have some expression that just has t's and k's or m's in it. Like it won't have anything but t's and k's and m's and numbers in it. It'll be an expression. And I'm going to stop until I want in the direct chat, right, you've lost me. Oh, awesome. I just got one. Okay. Things are happening in the direct chat. I'm so pleased. I'm excited and relieved. I'm not saying whether they're right or wrong just yet, but I'm saying there's at least two things in the direct chat. And I'll definitely say this. The two things in the direct chat definitely show that the people definitely understand the question I'm asking. Like they are answering my question, whether it's right or wrong. In fact, since it is the direct chat, thank you for following my instructions. I'm even going to say that two people in the direct chat are completely correct. You two that are in the direct chat, you are both awesome. I love you platonically, academically. I want you to submit for points. That's awesome. I'm still going to wait for other people. I'm not saying what, and thank you for doing it directly. So it didn't spoil it for other. That's awesome. You should, there's another person in the, very close. Oh, person who just went in the direct chat, so close, super close. Maybe just think about a little, like you did the first term correctly. Person in direct chat who, I'm not going to say who you are, but person in the direct chat. And also, please remember, guys, you could submit these for so many different portals of points. And any of you who happens to get a wrong answer, I'm almost even more proud of you because you have the guts to try. And remember, there's a special portal just for wrong answers where you get extra points. So don't worry if your answer is wrong. And if all of you were wrong, I wouldn't be mad. I would know what I had to teach next, right? It's all in the direct chat. There is no shame. But the more feedback I can get from you, the better. So there's at least one not entirely correct answer in the direct chat so far, but I'm just going to ask that. Okay, now there's at least two answers in the direct chat that are not entirely correct, but definitely show that you know what I'm asking, and I'm proud of both of you. Or three, hold on. Wait. Oh yeah. And now someone just asked something in the direct chat. Yes, K is a constant in this example, as is M. They are, you treat them just like they were just, and that's a great question. You treat K and M as though they were like numbers, like 4 and 7 or whatever. That's correct. T is the variable. You treat it like it's X. Everything else on the right side is a constant. You treat it like a number. And in short, to people, more people are in the chat. I'm glad, and this is good. Look, we need this review, folks. Do not be ashamed. Be ashamed if you're tuning out. I mean, don't be ashamed. I mean, I hate shame, but just as long as you're tuned in, you're where you need to be. And if every single one of you was wrong, I would know that we need to do something, and I would know it's not your fault. It's not about fault. Just give me something. So some of the answers I'm getting are right, and some of them are wrong, and that's good. And I'm just going to remind all of you, especially people that maybe are struggling a little bit, like we're really talking about here's power rule for derivatives. Right. You're going to do it on the first term and you're going to do it on the second term. Like the sum of the derivatives is the derivative of the sum, right? So just go term by term. In the top right thing, you're taking a derivative. And I'm not going to respond to each one of you in chat just because we're starting to run out of time. But I mean, I am looking. Oh, awesome. Person who just said, I got it. You are correct. You do got it. And I'm very proud. Yes, person who just said, I got it. You do got it. And you double and you thought it through. That's awesome. And person, okay. Yeah. Yes. Oh, if you're in the direct chat at all, awesome. Almost every one of you, actually, I think every single person in the direct chat, there's one person who's just about there, but just didn't deal with the M term. One person totally got it right, but just go one step further with the term that has the M in it. Like think to yourself, if the expression were, if y equals 5x, then the derivative dy dx is 5, right? So if the expression is x equals mt, that the derivative of that is not 0. If the expression were x equals m, then the derivative would be 0 of that term. But it's mt, so let me just see if I think we're almost very close. No, you were close to the wait. Hold on. Okay, wait, hold on 1 second. I'm looking at the time. I know we're running out of time. Hold on, sorry. So awesome. All right, if close, so close. Okay, I'm about to. Hold on. Okay, I will. If this were awesome. Okay, I'm looking at everybody's. This is great. And again, please submit these for points, even if, or especially if it turns out, I'm going to say, even if you have the wrong answer, don't worry. This is what we need. And again, it's really important that you guys are doing this because this little bit that I just asked you is like practice in differentiating. And by the way, believe me, I know I've been doing this for a long time. I know that for some, when you see the answer, some of you, the reason some of you are bumping or whatever is because you're used to everything being like y equals f of x. You're used to taking derivatives of x. What we have to start getting used to in physics, or you're used to having numbers. The thing is, physics is going to be a lot of calculus now, but the numbers are going to disappear, and it's not y as a function of x anymore. Generally in physics, at least at this stage, it's x as a function of t. So you are having to make a transfer in your brain. And that's why I keep screaming about independent variable versus dependent variable. I know that sounds very abstract and sounds like very wah, 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 or it sounds like very 7th grade, like you got sick of hearing about independent, dependent 7th grade, and then but I have to keep saying that. Every time I say independent, I'm really asking you to think of what you think of in math as x. And every time I say dependent, I mean what you think of in math as y. But I'm saying here in physics, we're much broader than that, like, or we're much more narrow than that. Like, this is independent, this is dependent. And to cut to the, so I think we do need this practice. Like, you got to stay with me. You got to practice these derivatives and integrals, because what I'm teaching you now is a step higher than that. And don't worry, don't lose faith, but do be honest with yourself. Like, I know personally, I never learned, like, I didn't learn undergraduate physics until I was forced to by accident when I was doing graduate level physics. And I didn't learn graduate level physics until I was forced to by accident when I was teaching physics. It always goes like that. You never learn the thing while you're doing the thing. You learn the thing while you're trying to use the thing to learn the next thing. It's always like that. So don't be ashamed of yourself, but do realize that we got to really finally start doing some calculus here. And we're going to do it through these differential equations. So what am I yammering about? Oh, wait, let me just look at the chat now. Okay, cool. Great direct chat people, especially who stayed with me and had a conversation. Great. Okay, so here's what I'm saying. First of all, I'm saying that the derivative, I'm looking at the time, I know we've got 4 minutes. I'm saying the derivative of that function up there is actually kt plus m. The derivative of that function up there is kt plus m. I did power rule on the first term, like I multiplied by the power, and then I brought down the power, right? So 2 times 1/2, and then I brought the exponent down to power 1, so I got kt. Then I did it on the next thing also. Like, the derivative of mt is just m. It's like the derivative, right? It's like the y equals mx plus b. What's the slope of the line? It's m. I mean, right, just happens to be an m here, but I could say that more slowly next time, but that's the derivative of the next term. But now I'm going to take the derivative of that again, and I'm going to cut to the chase because we are running out of time. I mean, maybe, well, I should have asked you to put in the chat, but the derivative of that, if t is the variable, right now the derivative of that is just k, right? So I just, that's the second derivative of 1/2 kt squared plus mt. K is a constant, right? The expression is k. Now, what does that have to do with anything? Like, I might have lost a lot of you because we went on this, but what am I doing? I'm trying to find an expression for x such that when I take 2 derivatives of it, what happens there? Well, m, oh, good question in the direct chat. The reason the m went away when I took the second derivative, see, m is just a constant. It's like a number. Imagine m just stands for the number 0.3 kilograms, right? It's just a number. So the derivative of a constant number is always 0. Like, if you just think of it as a function, if the function is just a number, if it's just a horizontal line at the value m or at the value 0.3 kilograms, the rate of change of that function is it's not changing at all. The slope of a horizontal line is 0. I don't know if I'm saying this kind of quickly because that's a great question. And please tell me in the chat if you want to hear more about that on Wednesday or if I did answer it. But I'm saying the derivative of a constant is always 0. So technically what I'm writing here is k plus 0. Yeah, oh, okay, cool, great, and thank you. You get, please submit that for all the kinds of points. Seriously, I feel like this is a class now. Now, here's why I did all that. Partly for practice, we need practice with derivatives, but because I was testing my function, I guessed a very reasonable function. I guessed that x was 1/2 kt squared plus mt, but I took 2 derivatives of x, and I didn't get back 1/2 kt squared plus mt. I didn't get back that whole rule times k over m times a negative sign. And I didn't get back an x. I just got back this letter k. In other words, when I took 2 derivatives of it, I just got a constant. I didn't get the original function. There's no t in the expression, and there's no x in the expression. There's no so I didn't. So this doesn't follow. This was a good guess, a good reasonable guess, but it was not a solution to the differential equation. What I'm showing you right now, I'm saying with 1.5 minutes left, to solve differential equations is to do reverse engineering. You're looking for a function that does something. You're not doing something to a function. You're looking for a function that does something, okay? And the way we do it right now is we make educated guesses, but then we check. The checking is the straightforward part. You guess a function, and then you take the appropriate number of derivatives of it and see if it does what the differential equation said. This guess didn't work. But if I make a different guess, again, where did I get my guess? Like we wanted this, but we got that. That did not work. It was not a solution. It was not a solution. Like all of homework 2 is about. Is it a solution? Is it not a solution? It's not a solution if it doesn't fit the equation, the original differential equation. But if I guess something with a cosine in it, where did I guess cosine? I guessed it from the lab. And right? I get, and again, don't worry about the thing in parentheses for a minute, but just remember, cosines now are those type of functions. If you take the derivative of, and I know we're just about done. If you have to go right now, go, but I'll be done in 60 seconds and I'll stop for any questions, but I'm about, just listen to this for 1 second. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. So when you take two derivatives of cosine, you do get back the original function times the negative sign. So cosine does look a lot like what we're looking for here from the lab and from my mathematical experience with functions. The only thing is I'm supposed to get back something that is multiplied by negative and multiplied by k over m. So I think chain rule backwards. If I stick a square root of k over m in the cosine, right, just if I take one derivative, now I'm doing this fast, I'll do this more slowly on Wednesday. Don't freak out if this is too fast for you right now. But just so those of you who can see the ending of this, that those of you who can follow, if you take one derivative of cosine, you get negative sine. And with chain rule, the square root of k comes out. Chain rule, I'll review chain rule on Wednesday. I will. But if you remember it, you know that means the derivative of the inner gets multiplied by your whole expression. So then I do that again. And the derivative of negative sine gives me negative cosine, and the chain rule brings out that square root again. So I literally do get negative k over mx. That expression, this expression is what actually works. And if you plug in the appropriate numbers there for question 9 on homework 1, you get 0.116. What I'm telling you right now is how you check your guesses. Where I got that guess from, I'll explain in more detail on Wednesday, but that's the actual answer to the differential equation needed for question 9 in homework 1. So x equals, 0.15 times cosine of square root of 200 over 0.3 times 1. If you plug all those in your calculator in radian mode, you'll get the right answer, which is 0.116. Thank you for staying over with me in those 2 minutes. Sorry, I'm done. You've been awesome. Keep working on homework 2. I'll see you Wednesday, but I'll hang out for a second if there's any questions. But thank you.
Have a good day, Professor.
You too. Have a great day.
Thank you.
Thank you. Okay, I'm changing. I'll turn off the recording, but thank you guys. Oh. Oh, yes. Okay, hang on 1 second. Yes, hang on wait, let me turn off the recording. Wait.